Alright, so the third set of batteries is now working. So just in case the previous stuff was missed, so the reason we were playing Van Halen's Jump was we want to be able to quickly look at things and see, are there mistakes? We want quick checks, and this was the whole point of the brown M&Ms. You could quickly look at the bowl and see, are there any brown M&Ms? That's probably not the color I would have chosen, but that's not the real point. So here, one thing is to know what the Superstar Destroyer looks like at certain stages. And so, what kind of property does the Superstar Destroyer have for the most part? Symmetry. So that's going to be a huge boon for us in terms of trying to see, have we made a mistake? Different sides are supposed to look symmetric in terms of how things are falling. Are they lined up? Some of the really hard parts is there's these almost like hook pieces, almost like little Lego hands. Do you have them off by 90 degrees? And in some places, some of them go this way, some of them go that way. It's mostly consistent. Small things like that, we've got to be very careful about. We can then have discussions as to whether or not a mistake like that counts as an incorrect build. To me, that's very minor. But you want to have stuff like that. You want to know roughly how far down should something be. Are there quick checks? I think what happened with one of the wings last year is when they dropped it, they then tried to rebuild it and they were off by one row. And being off by one row, then they were having trouble and they were trying to figure out where is that one mistake. This is one reason why it's nice to modularize things and break things into smaller units. The smaller the thing is, the easier it is to localize the mistake. If you think about programming and trying to find mistakes in computer code, the longer your code is, the harder it is to find where your mistake is. You want to have lots of different checkpoints. So the more checkpoints you have, the easier it's going to be. And so I wanted to use that as the motivation for the little bit of lecture today. So does anybody remember what I believe is one of the greatest inventions of the 20th century? The scanner. So the scanner is absolutely wonderful. And it is amazing what the scanner is able to do. How does the scanner work? Scans a barcode. And in fact, out of curiosity, how many of you have scanners now on your phones? So I mean, now you actually have your own scanner. It's not just the people at the supermarket anymore. What happens in this catastrophe of a world where it scans and it doesn't scan it correctly?
You get it for free.
I got to go shopping where you shop. I do not get it for free if they scan it and it doesn't work. They try again. And usually on the second or third try it works. So this is a big thing in terms of error correcting, error detecting. If it's very easy to try again, you don't need to be able to correct errors, you just need to detect errors. So this leads into the subject of cryptography or information transfer. How many of you have ever watched streaming video? For those of you who have missed some of today's class or some of the classes here, that's a great example. The way streaming video works is you do not send every pixel. You might send a couple of key, maybe take like a Taylor series or generalization of a Taylor series, a Fourier series, or wavelet analysis of the image, and then send different updates. And then you use the fact that you have smart computers on both ends. So the computer can take a couple of those coefficients and build together the image of what's going on. So you don't have to send each pixel, you can send how things are changing. If you look at file sizes for when I lecture, the more I move around, the more the file takes, because it's not really transmitting that much changes in certain areas. And so it's really interesting to see how something like this is done. How much information do you have to detect? When you're downloading a file, if it's a large file, it would be terrible to have a small mistake somewhere in the middle and have to download the whole thing from scratch. So there's a lot of systems that do information transfers where you are detecting and correcting errors. It's nice to be able to correct the error as you go along. And so if people are interested, I will give you some links, I think, to read about how you would easily correct and detect errors. What I will do today is I'll just give you the simple case of how you can detect errors. Obviously, the more complicated system you use, the more errors you are able to detect. And the more complicated system you're able to use, the more errors you are able to correct. So let's do simple error detection. And again, this is extremely important for what we're going to be doing in terms of the build. So one of the simplest things is looking at UPC, so Universal Product Codes. Anybody know the very first UPC? If I really cared, I would have looked it up.
0.
No. Sorry, what was the first product? Where was it? When was it? How long have they been around? My wife and I went to Hawaii for our honeymoon, and we saw a coffee plantation from the 1850s, which had UPCs on them. I commented to the historical director that the site was probably not accurate, that in 1850s Hawaii they did not have laser scanners. I think the first was from the 1970s. I think it was like a pack of Wrigley chewing gum from some store in Ohio. So we're now around 40 years of stuff like this. And so there's lots of different ways they work. And so you frequently have a string of numbers, 3, 4, 2, 8, 1, 1, 7, 2. And you have different barcodes, and it was a fascinating story as to how they finally chose the different barcodes. If you look at the scanners we now have on our phones, I think the images, I don't use them too often, they have, I think, 3 squares like this. Why do they have 3 squares like that? Yeah, for alignment. So you don't have to be that smart. You just have to move things back so that your 3 dots go in the 3 dots there, and now you're doing it at the right level. So very small ideas like this are phenomenal. And this is one thing. Again, billions of dollars of savings in a year, building a superstar destroyer in 10 minutes or less. These two are not comparable goals, but you want to get into this mindset: how can I do things well? And so over here, let's say you scan something like this in, and let's say you accidentally read 34181172. And instead of charging you for a pack of chewing gum, it's charging you for a new car. Okay. Usually that's not going to happen because stores that sell chewing gum are not usually selling new cars. But it could be maybe it charges you for a computer. And so you could be off by 3 orders of magnitude. Hopefully you are checking your receipt before you leave, and you would notice something like this. So the question is, how can we detect errors like this? One of the things we often do is we have what's called a parity digit, or a check digit. And so right now, it's what? It's about 10 o'clock. What time will it be in 5 hours? 3. So, I said there were very minimal math prerequisites for this class, but you're telling me 10 plus 5 is 3. If you're using 24-hour time, it would be 15. But on normal 12-hour clocks, 10 plus 5 is 3. So in math, we often put 3 equal signs here, and we might put a 12 in parentheses to say that these two sides differ by an integral multiple of 12. And this leads to modular arithmetic. This leads to abstract algebra. This is extremely useful. For a lot of purposes, 15 and 3 are equivalent. Right? Not in everything. If you make a $3 deposit or a $15 deposit, there is a difference. But if you want to say 3 o'clock or 15 o'clock, they're the same. 15 o'clock gives you a little bit more information. If you say 15 o'clock, I know we're talking about 2 p.m. 3 p.m. Whereas if I say 3, I don't know if it's 3 a.m. or 3 p.m. We can do the same thing here. And one of the tricks is to look at this number and write the last digit, which will be the remainder when we divide by 10. It'll be the sum of the ones digits. So here, 3 plus 4 is 7. This is 10, so 17, 18, 19, 21, 28. So we would write an 8 here. And so now if we get this as the scan, we know something is wrong. Why is something wrong? Well, the check digit is not equal to the sum of these digits, divided by 10, what the remainder is. It's not equal to the ones digit of that sum. So there's a mistake.
Couldn't theoretically you get 2 digits wrong, including...
Absolutely.
Or something changes to a point where the check digit is actually correct?
Absolutely. And so other errors we could have is we could have 324811172. We could have 41481172. In these last two cases, it would pass the check digit test. So these pass the test. This one fails. So if I get this, I know a mistake has been made. What that mistake is, I'm not sure, but I know a mistake has been made. It all comes down to how likely do you think mistakes are to be made. If you have something that's extremely prone to error, well, then you may not be that confident about transmitting information through the medium. You should hopefully be in a situation where errors are rare. And so the probability of having two mistakes is hopefully so small that you don't have to worry too much about it. But there are more advanced procedures you can have, more complicated things that will actually detect sometimes when there are two digits that have been switched, or when you have multiple mistakes. Unfortunately, what do you think is true to detect multiple mistakes? Usually it's a harder computation. Usually you might need more check digits. And the more check digits you have, the less information you're transmitting and the more checking you're doing. And it depends on the situation. For the barcode isn't that big. It's not so bad to put in a little bit of extra redundant information. One of the most famous systems is the tell me 3 times. And if it's very rare to make a mistake, if you are asking the system to tell you 3 times, let's say you get A, and B. What do you think the right answer is? A, right? And a lot of times, the military uses this when they do firing coordinates, is they have 3 computers calculate what the firing solution should be. If 2 out of 3 agree, sure, blow it up. Okay? And your odds are pretty good if 2 out of the 3 get you the same answer that you're right. Has anybody seen the movie Minority Report with Tom Cruise? So this is a nice, interesting example of 2 out of 3. And you can't have situations where maybe there are multiple mistakes being made, but they cancel, or they get you to the same answer through different wrong calculations. So again, the more checking you do, the better, the more confident you can be about the answer. Sometimes you can actually do calculations that might seem like they're going to take more work, but actually take less work by just grouping things well. And so I'll leave check digits right here and just quickly talk about maybe efficient calculations. So let's say I want to calculate 3 minus 1 plus 14 minus 3 plus 88 minus 14 plus 1701 minus 88 plus 24601 minus 1701. What's the answer? Yes? What's the answer? 24,600. Jean Valjean's neighbor. Okay? How did you get that so quickly? So you can cancel. And so rather than doing things horizontally, rather than doing a bunch of sums and adding them, we notice that there's a lot of cancellation that goes on as we go down. And so this has enormous impact for what we're doing in this course. Just because you're given a linear set of instructions, just because you're told to do something in one given way, does not mean that is the way you should do it. It is so easy to get blinders on you. For those of you who have never taken a math class, depending on how we write the questions, we can either make sure you get the question right or get the question wrong. It's very easy to do. And we can just get you thinking in certain directions. I know this is being recorded, but I'll risk telling the story. My favorite exam question that I ever wrote was when I was teaching abstract algebra at Brown. I am a math major who has never actually taken abstract algebra, but I've taught the class a few times, so it's almost as good. And so there's a concept in mathematics called a ring. And if a ring has a certain additional property, it's called an integral ring. So part A for 5 points was I asked the students, is this set a ring? And part B for 15 points, I asked them, is it an integral ring? It wasn't a ring. It failed one of the basic properties of rings that are almost always met. And so often met nobody bothers to check. 2/3 of the student wrote, the answer to A is it must be a ring, else why would you ask B for 15 points? It's very easy to get into a certain mindset and to attack a problem a certain way. You want to get to the point where you can step back and look away from things. To some extent, having the directions in front of you is a bit of a disadvantage. You almost want to just look at the picture and think, how would I build this if I didn't have the directions telling me this is how to go through it? I think one of the best examples for what we're doing is the wings. And so, I am a horrible artist. I don't know, was the wing going, I think then it's coming in like this maybe. One of the wings I think looks something like this, roughly. And so the question is, in the book, it's being built linearly like this down the road. It might be better to have one person building like this and one person building like this. Or maybe one person like this, one person like this, and one person like this. And then worry about how you overlap and connect. Because again, we just care about getting to the final stage. We don't care about the path we take to get there. And so it's so easy to have these blinders on. You need to be able to step back and think, how should I approach this? So to me, the telescoping sums is a great lesson in terms of you can have a calculation that looks like it's going to take a lot of work, but if you arrange it in a slightly different manner, it's significantly less. All right, any questions? All right. Just so I don't have to upload, we're going to just redo the very first part of the class lecture now, because it's just such a pain in the ass to deal with OIT right now, and I don't mind if this is recorded, that I just want to have one video that I have to upload and not two. So I am replaying, what song? Jump! Yes, by? And why are we playing Jump by Van Halen? Because of the brown M&Ms. And so they had an agreement when they did concerts at third tier locations that if there were brown M&Ms in their dressing room, in their bowl, they had the right not to put on the show and still collect full salary. And the reason is they did this as a really simple, quick way to check and see, was the contract read and honored? And that's what we want when we're doing the Superstar Destroyer. We want quick checks to be able to glance down. Symmetry, we said, was a really big one for us, and see, is everything being done right? Okay, so I'm going to hit stop now.